Okay, perfect. So now you can see your, okay, yeah, that's
okay,
good.
thank you. Thank
Perfect.
you.
Okay, so Veronica, the floor is yours. You may
Thank
start.
you very much. Thank you for the invitation. It's an honor to be here. Today I'll talk about work I've been doing with my supervisor, Professor Fernando Quevedo, related to this article that came out a couple of months ago. So today I'm going to talk about the holographic interpretation of two-dimensional vacuum transitions. So the outline is the following. First of all, I'll tell you something about the motivations that led us to discuss about this topic. Then the two different methods that we used, the Euclidean and Hamiltonian, in particular Kolmogorov and Brown-Teitelbaum, and Fischer, Morgan, and Polchinski, for calculating the amplitudes for the transitions. And then I'll outline the holographic interpretation of the results. So the motivations, first of all, the population of the string theory landscape, because most models account for anti-de Sitter or Minkowski as the four-dimensional part of the string theory setups, plus compactifications. So addressing the stability of anti-de Sitter is a natural question arising in string theory. Studying transitions is also a promising setup for understanding quantum gravity at the same level of black hole physics. In fact, there are similar unitarity issues with respect to the information paradox that also arise in the context of vacuum transitions. And as I'll show you today, it's possible to give an entropic interpretation to the bounce or the total action described in the transition without the need to resort to detailed balance to assign an entropy to the different spacetimes that are being involved. So from the holographic perspective, the tools that we're going to need are the following: anti-de Sitter boundary conformal field theory, wedge holography, TT bar deformations, de Sitter correspondence, specifying in particular to the 3- and 2-dimensional correspondence, and the island, because as you for sure know, it's one of the most extreme formulations of the holographic correspondence, because it involves space-time regions that are causally disconnected. And as you will see, this will arise in our setups as well. So today we're going to see how all of these topics are going to emerge naturally from our results. So this is just a very basic recap. Obviously, the audience is well aware of all these tools, but just for completeness, I'm going to outline them. So holographic entanglement entropy basically is a tool that enables you to perform bulk reconstruction, because from the Ryuta-Garanaki prescription, by knowing the entropy of the boundary, you're able to bulk reconstruct a portion of the bulk. So the key relation is the one in between the entropy and the area, just as the previous speaker discussed thoroughly. So this is the basic at the heart of the holographic correspondence itself, but there's something that goes beyond this, and this is the context of black hole evaporation. Because in the embedding in the holographic setup of the black hole evaporation processes, such as the one that you can see here on the left, you have a black hole evaporating on an end-of-the-world setup. This is the Cartwright-Hartmann-Mandel-Senna construction. And there are two parameters that dictate the time evolution of the process. And it's basically the ratio in between the two central charges, the one associated to the boundary defect and the one of the bulk CFT. Now, as the two regions are basically assigned to the black hole evaporating, which is the defect, and the conformal field theory, which is instead the part where the bath is, or basically the observer lies. So as time evolves, these two parameters, the two central charges, mutually interchange, and as a consequence, the degrees of freedom flow. So from this flow, there's a change in the domain of the saddles that characterize the partition function for the radiation of the Hawking radiation that is detected on the bath. So the Ryuta-Garanaki surface, which initially just ends up on the event horizon of the thermofield double, now intersects the end of the world brane, detecting the island, which is the red part that you can see here. And so this additional part, this boundary, the boundary of the island, is an additional term that adds on top of the usual entanglement entropy that characterizes the Ryuta-Garanaki prescription. So that setup, which was the original one, where the bath is non-gravitating, it's placed at conformal boundary with z equal to 0. Now, the main issue of this one, which is the first formulation of the island in holographic setup, had the fact that the graviton was massive. So to avoid this, you need to resort to introducing a gravitating bath instead. So you basically need to apply deformation to the conformal field theory, and this deformation then allows you to flow, allows the conformal field theory that lives on the boundary to flow, and flowing, you end up in this other configuration, which has a gravitating bath, because there's a reduction of the degree of the dimensionality of the boundary. So you're left with this defect alone, which is now the boundary of two end-of-the-world branes. And this is where the wedge holographic picture emerges. So now, basically, you've resolved the problem of the massive graviton, but there's another one emerging, which is, as Raju, Karsh, and Randall and other collaborators have argued, is that you have a plateau in the entanglement entropy. So there's no page curve emerging on this setup if you calculate entanglement entropy on the second end-of-the-world brane, which is the gravitating bath. Instead, a page curve can still arise as long as you perform the calculation of the entanglement entropy on the defect that lives on the what is left of the conformal boundary, which is one dimension less. So it's codimension 2 with respect to the bulk. Now, if you perform the calculation here, being some kind of sub-man with respect to the original dimensionality, now there is an emergent page curve even in this setup. So this solves the problem. And this introduction of the TT bar deformation, which is basically what I just described in words previously, this is key to our analysis, because as we will see, we will relate the action precisely to the action of TT bar deformed CFTs. Now, another key ingredient that, as we will see, will be very important is the boundary free energy. Now, the boundary free energy, as you obviously know, is defined as being the universal term of the boundary entropy, which comes as the limit when you remove the cutoff of the ratio in between. This is the Cassini-Huerta-Myers prescription for determining it. When you have a boundary CFT and you have a defect, then you just take the ratio of the partition functions evaluated on the half sphere with the defect with respect to the half sphere without the non-trivial boundary conditions. In 2 dimensions, this expression reduces just to the interface conformal field theory entropy, which is minus the boundary free energy. And we show that this is equal to the difference of 2 TT bar, the universal part of the difference of 2 TT bar deformed entanglement entropies. Now, why is this relevant for us? For vacuum transitions, I mean. So the relation between islands, horizons, and vacuum transitions can simply be recast by this first observation. One long-standing issue is understanding what is the entropy of de Sitter, and it's still an open question. So the reason for this just comes about, for example, if you analyze up and down tunneling in between 2 de Sitter spacetimes. This was originally formulated in 4 dimensions. Coleman de Lucia analyzed the down tunneling process, then Lee and Weinberg extended it to up tunneling. So they argued that the detail balance, which is basically the ratio in between the 2 transitions, up and down transitions, lead you to this expression that is an exponential of the difference of 2 terms. Each one of them can be associated to the entropy of the de Sitter being involved. So this can actually be intuitively assigned to the entropy. So the entropy is assigned to the Hubble parameter characterizing each spacetime. Now, when you take the flat limit of the background spacetime, this ratio diverges. So it basically tells you that the transition is forbidden. But this is somehow counterintuitive, because if you see de Sitter in dimension bigger than 2, which is in the global de Sitter, is pictured in this, is drawn in this figure here, you can think of the static patch, which is the one associated to the Hubble parameter, as being just this green quadrant, and this wedge. And this wedge is has the boundary, which is obviously the where the cosmological horizon is placed. And you can think of the entropy that is defined on this static patch as being the result of having traced over the rest, the other quadrants, which is exactly the prescription that you would use to define the entanglement entropy in the context of just pure setups. So if you take the flat limit, this boundary is supposed to extend towards square plus. So taking the limit is equivalent to reabsorbing the degrees of freedom that you've traced over. So you should assume that once taking that limit and taking it to 0, so you take infinity, h to infinity, so you take lambda to 0, as a consequence, you should end up having 0 entropy, because you are the observer, which is placed here at I equal to 0, should be able to access all the degrees of freedom of living in global lucidity. But this is not true. So this is probably prompting the issue that the entropy is not simply 1 over h squared in 4 dimensions, but it might be something else. So this was the first motivation to see whether we could address the problem of assigning an entropy to de Sitter or all spacetimes without the need to resort to detailed balance, which highlighted this problem. So the 3 methods that I used to determine the amplitudes are 2 Euclidean methods, Coleman-DeLucia and Brown-Teitelbaum, and the FMP, which is in Lorentzian signature. So Brown-Teitelbaum is basically a standard ruler for this calculation, because the calculations were already performed by the authors in their original work. So basically the new parts are just the Coleman-DeLucia and FMP calculations. So first of all, the WKB approximation is what we're going to need to calculate the tunnel in 2 dimensions, because starting from the Schrödinger equation in 2 dimensions and assuming that the wave function is an exponential of the action, and expanding the action to leading order in h bar, at 0th order, plugging this back inside the Schrödinger equation, we get the Hamilton-Jacobi equations. Now, assuming that the wave function is an eigenfunction of ng, we can obtain an explicit expression for the action to 0 order, and assuming that the energy is smaller with respect to the potential, we get this final expression, which enables us to define the decay rate, which is a function of b, which is the bounce. So basically, in the Euclidean calculation, the bounce is the key quantity to calculate, and it's always defined as the difference in between the entropy, the action calculated on the instant in solution to the equations of motion, with respect to the action calculated on the configuration. Now, for CDL, there are 2 ways to do that, either with or without gravity. Without gravity, you just end up having. Sorry, what is this? Okay, thank you. So with gravity, we just end up having the total bounce, which is the bounce associated to the standard Schwinger pair production of particle-antiparticle pair in a flat background. Adding gravity, we use the Medici setup, and we use 2 different procedures, thanks to the triviality of gravity in 2 dimensions. Sorry, not triviality, I should have said, thanks to the particular features of 2-dimensional gravity. We are able to trade the kinetic term for the scalar field with the one with the Ricci scalar term, and so we are able to get 2 different results. In the first case, when you remove the kinetic term, we have two different procedures, either the thick wall method or the thin wall approximation, and we obtain these results for the total bounce. By removing the Ricci scalar instead, we end up having something which is like the Brown-Teitelbaum action up to a boundary term, which is a term that you need to add by hand. And this boundary term is important as also Brown-Teitelbaum stress, because this comes in order to ensure that you get a good variational principle. Now, in the Hamiltonian formulation instead, which is Lorentzian, we're using JT gravity in 2 dimensions. And this is the Lagrangian density. We have the Ricci scalar, cosmological constant, the brane term, and two constant terms that are very important, and these are added on top of the JT setup. And these two constant terms are going to play a central role in determining the geometry of the space-time. Now, in the Hamiltonian formalism, we need to introduce the Hamiltonian momentum constraints. So this means that the formalism is precisely microcanonical because we are fixed in the energy. And by integrating over the constraints, we end up having this box expression, which is like an energy momentum, an energy conservation law. And we are able to determine the turning points by setting the kinetic term of the field to 0. So when the case where B is different from 0, we end up having two turning points rather than just one, and this is precisely the signal of the emergence of a black hole. So B is playing the same role as the mass of the black hole in space-times, and this can also be shown explicitly by determining the equations of motion, and the solution gives us this metric that you can see here that precisely introduces an additional root to the metric function. These are the basic results that we obtain in the Hamiltonian formalism. And now what I'm going to show is what is the holographic interpretation of all these. First of all, Brown-Teitelbaum, which is, as I said, is the standard ruler for our setups, is basically a type 2 Einstein-Maxwell Dalton gravity, because the action is characterized by a Dalton which is coupled to both the Ricci scalar and the gauge field. And so this is different with respect to the type 1, because in the type 1, the coupling is just in between the Dalton and the Ricci scalar and not the gauge field. So this is precisely the setup where I was mentioning we have B, the constant B would be this one. And so both admit an ADS2 solution which is dual to a CFT1, but only type 2 descends from an ADS3 CFT2. And precisely this can be shown by looking at the central charges. So this suggests that there might be this new perspective of assigning an entropic interpretation to the action itself rather than resorting to detail balancing to do so. And I'll also show now where the possible island interpretation emerges. Now, FMP, so the Hamiltonian method, allows us to determine a final result of the transition, so the total action, which can be recasted to the difference in between two TT bar deformed CFT entanglement entropies, which in turn is equal to the difference to minus the boundary free energy, as I was mentioning earlier in the Cassini-Huerta-Meyer's prescription. And also this is basically done by mapping one-to-one all the parameters featuring in the action with the ones that were made in the calculation by Hermann Berlinde for ADS CFT and Silverstein et al. For the SDS. Now, the emergence of the island comes about when the parameter that I was mentioning, the new parameter in the Lagrangian, so B different from 0, enters into play. Because in this case, we have a type 1 Einstein-Maxwell Dalton gravity, and in this case, we have an island emerging. So we can take the flat limit, and in this case, there's no divergence. The action is finite, and the transition as well. So this allows us to define uptunneling and downtunneling, including Minkowski in the setup. And this is an example of an ADS2 CFT1 which is not encoded in ADS3 CFT2, which is precisely the signal of an island emerging. On the other hand, for Brown-Teitelbaum, the total action can be rewritten as a difference of different terms, one encoding the entropy of a CFT2, and then two boundary terms, two boundary entropies, which are assigned to the two endpoints of the CFT, which is basically the geometrization of the brane action that mediates the nucleation process. And the two end-of-the-world branes instead can be thought of for the ADS transition as being the two regions where the two spacetimes are placed. And what divides them is what remains of the CFT once it's brought at a finite cutoff by the action of the TT bar deformation. And so this black line with the two endpoints is precisely the brane action once you visualize it as being the RD flow that connects the two minima characterizing the two spacetimes involved. On the other hand, for the case of Kalman-Deluccia, in the thick wall analysis, what we end up with is the total bounds for ADS to ADS being equivalent to the product of two Cardi entropies. In the degenerate case, so in the case where they're both equal, and so this Cardi entropy is given by the square root of terms involving both the central charge and the excitation energy of excited states. So this is telling us basically by looking at what these parameters are mapped to in the transition, the central charge is mapped to the background cosmological constant, and delta instead is mapped to the new cosmological constant of the new spacetime being nucleated. So this is telling us that you can actually visualize the nucleated spacetime as being a black hole in the background spacetime that you started with. So it's in this sense, you can think of it as being like some kind of relative entropy. So this is basically the summary of in terms of notations. You have we were able basically to encode a correspondence between the different methods as long as B is different from zero, as long as B is equal to 0. So you have no black hole mass. But when B is different from 0, we were able to give an interpretation of the total action as being the difference of two generalized entropies, where an emergence of an island is can be identified, and this is given by the value of the dilaton on the boundary of the island. So you can actually see that by tuning B, which is you're actually able to detect by looking at the brane action, a phase transition, which is signaling the presence of an island, because from a certain value of B, which is the black hole mass, where the entanglement entropy has a minimum, at some point this minimum vanishes and it becomes just a monotonic function. So this means that beyond a certain value of B, which is after the black hole has evaporated up to some point, the mass has shrunk at a point at which you need to introduce an island in order to recover a minimum for the entanglement entropy. So I just wanted to highlight before concluding that the importance of the scales in the limits. So we basically need to introduce a new scale, which is the black hole mass B that I quoted. And as the next speaker will discuss thoroughly, this is very much like the idea that you need to introduce two scales even for the case of the double scaling SYK model, when you try to give an entropic interpretation to de Sitter not in the static patch, but in a subregion. So in order to do that, you need to introduce these two parameters and take both the limit of both. And this is very much in the spirit of also what Schlenker and Witten did recently in the context of connected amplitudes with disconnected boundaries, in order to reconcile them with the holographic interpretation, which is the same thing that we did as well. Furthermore, I would also like to stress an emergent entropic hierarchy. You will find plenty of comments on this on the paper, but I can just go very quickly because I'm already out of time, I think. So the thing is this: basically, in the CDL context, we showed that the total action described in the transition is associated to some kind of relative entropy, holographically speaking. So you can think of it as being like the entropy associated to a type 3 von Neumann algebra, because just in the same sense that you need that in that case you can't define a von Neumann entropy, but you can still define a relative entropy. Then for the case of Brown-Teitelbaum and FMP without a black hole, the total action is given by the difference of von Neumann entropies, and this is mapped to a type 2 infinity von Neumann algebra, where you still have infinite entropy. But in fact, as we showed, in this case, if you take the flat limit, the entropy still the total action still diverges, just as in the von Neumann type 2 infinity, there are states that emit infinite entropy. On the other hand, when B is different from 0, which is the additional that you add by hand in the Lagrangian density. This gives us the chance to take the flat limit safely, and this is like acting with a projection operator on the von Neumann algebra, so that we're led to a type 2-1 von Neumann algebra, where instead the definition of a maximum entropy state can be given, and precisely that is what you need in order for islands to emerge, because once you've identified what is the maximum entropy that the state can have, the exceedant entropy must be explained by introducing an island in some way. So this is the same thing that we needed to do basically in our setup. But we don't know what a type 1 von Neumann algebra would be equivalent to from the point of view of the transition amplitude, so this would be an interesting thing to further investigate. So this is mainly the results that we get. We've proved the complementarity of the holographic interpretations by giving an entropic mean to both the bounds and actions in the Euclidean and Lorentzian signatures. The flat limit of two-dimensional vacuum transitions always requires a black hole. Black holes play a similar role as TT-bar deformations in a CFT2. The black hole mass is related to the cutoff of a CFT2, just in the spirit of the TT-bar deformation that I was mentioning. So you need to keep the TT-bar deformation in order to make the transition local, and this is mapped to requiring having a black hole mass. The total action for the Brown-Tatum and FMP calculations were proved to be always equivalent to, recast always to the difference of two generalized entropies, a la Maldacena et al., where the entanglement is understood as being internal, and uptiling from either anti-de Sitter or Minkowski in 2 dimensions requires islands. And so we hope that this analysis will stimulate further investigations in any of these topics. And with this, I'm finished, and I thank you for your attention. And I'm happy to take any questions.
Thank you very much, Veronica, for this nice talk, and also for keeping the time limits. So I think we have time for questions. So does anyone want to speak, or you can write it in the chat?